Episode 4. Title of the Radio-Enable Learning course is Energy Physics, Unit 1. In this episode 4, we will discuss about nuclear energy. A form of nuclear energy released by the fusion of two light nuclei to produce a heavier nucleus. For two nuclei to fuse, they must come close enough to interact. However, similar electric charges repel one another, and since all nuclei carry a positive charge, an increasing force of repulsion develops as the two nuclei are brought closer together. Consequently, for the nuclei to fuse, that must have enough kinetic, that means motion, kinetic energy to overcome the force of electric repulsion that keep them apart. For the force of repulsion to be small and thus make fusion easier to achieve, the interacting nuclei should have small positive charge, that means low atomic numbers. The element hydrogen has the lowest atomic number since the nuclei of its three isotopes all carry in single positive charge. Hence, hydrogen isotope, which also have the lightest nuclei, should be particularly suitable for the production of energy by the fusion of two light nuclei, that means similar to dissimilar, to form a heavier nucleus. The three hydrogen isotopes are ordinary or light hydrogen with a mass number of 1, heavy hydrogen or deuterium mass number 2, and tritium the mass number 3. Of the several possible reactions between pairs of hydrogen isotope nuclei, the fusion of deuterium nucleus or deuteron and a tritium nucleus or tritron has been found to take place most readily. This is referred to as the DT reaction and is expressed as D plus T gives 4He plus small n plus 17.6 mega electron volt, where 4He represents a common helium-4 nucleus and small n is neutron. The fusion of one deuteron and one tritron release 17.6 million volts mega electron watt of energy. Nuclear fusion could be called nuclear combination, that is, it is the release of energy that occurs when the nuclei of certain isotope of the light elements, that means H2, He, Li, etc., collide and fuse together at ultra high temperature, more than 10 to the power 8 degree Kelvin. This is the source of energy of the sun and other stable stars which burn ordinary hydrogen as their fuel. The main isotope being considered are the heavier isotope of hydrogen and some isotopes of helium and lithium. The primary fuel for fusion is deuterium, sometimes called heavy hydrogen, H2. Deuterium is a stable isotope of hydrogen that exists together with ordinary hydrogen. At the time of creation of solar system, deuterium was formed and was retained on the earth in the water of the ocean. There is one atom deuterium for every 6,500 atoms of ordinary hydrogen in water. This energy heritage has lied in store in the ocean for countless millions of years, waiting for mankind to learn how to release it. The total energy content of deuterium as fossil fuel is about 1 lakh kilowatt hour of energy per gram of deuterium. This is 4 times the energy released per gram in the fission of uranium and is about 10 million times that release per gram in the combination of fossil fuel. Today the total world energy consumption, that means all forms, is estimated to the 6 into 10 to the power 13 kilowatt hour per year. This entire amount of energy could be supplied by the fusion of only 600 metric tons of deuterium. To obtain this amount of deuterium, a deuterium isotope separation facility would require acid feed, stock the amount of water that would flow at normal water pressure through a water main only 50 centimeters in diameter. The amount of petroleum that would be required to satisfy the same world energy need would be 120 million barrels a day, a rate sufficient to deplete the world reserves in a few years. We can deduce that the amount of deuterium in the world ocean would be enough to sustain the present total world energy output for 100 billion years. That is 10 times the estimated age of our universe. Hence, it can be said without any doubt that fusion would indeed represent an ultimate solution of mankind energy needs for all the years to come. Fusion by one now has become a substantial international research effort. By 1971, Soviets have increased their research efforts in this field to the extent of about 38% of world effort. US effort is 16% of the total world effort. US at present spending a large sum of fusion research. The Japanese program, although starting from a smaller base, is now growing even more rapidly. In 1973, it represents 10% of the world effort. Fusion research is indeed being taken serious by the major industrial nations. The intellectual possibility of fusion power has been established, but many scientific and technical problems still remaining to be solved. Scientists of Princeton University, America have achieved success in controlled fusion reaction using mixture of deuterium and tritium. Before we discuss the basic of nuclear fusion, let us define and differentiate the two nuclear reaction, fission and fusion. The nuclear reaction that are likely to prove useful as energy source fall into two general categories, fission and fusion. In fission, a heavy nucleus is split into two or more lighter nuclei. In fusion, two or more light nuclei fuse, combine to form a heavier nucleus. In both, there is decrease in the mass resulting in the energy. Fusion reaction occur at very high temperature. First, we will discuss about fission. The fission process is accompanied not only by the release of energy but also the emission of neutrons called fission neutron. 2 or 3 neutrons are emitted on the average per nucleus undergoing fission. The emitted neutrons can cause fission in addition nuclei, thus liberating more neutrons which can cause further fission and also so on. However, for a self-sustaining fission chain to be possible with the continuous release of energy, certain requirement must be met. Neutron plus heavy nucleus gives fission fragments plus neutrons 2 to 3 plus energy. One requirement is that the heavy nucleus must be such that they can be fissioned by neutron of any energy. These substances are referred to a very important thing. The fission neutrons initially have a high kinetic or motion energy, but this decreases rapidly as the result collision with various nuclei. For a fission chain to be sustained, the neutrons of lower energy must be still capable of causing fission. This is possible only with most important things of the fission reaction. All fissile substances are radioactive, and to the useful as practical energy sources, they should have reasonably long half-lives so that they do not decay too quick. Furthermore, they should exist in nature in moderate quantities at least, or be capable of fairly easy production from available material. Only three important components those conditions: uranium 233, uranium 235 and plutonium 239. Of these three important components, only uranium 235 occurs in the nature. The other two are made artificially. An important aspect of fission as an energy source is that it can be self-sustaining process. A neutron can cause fission, which is itself accompanied by the liberation of neutrons. These neutrons can be cause further fission and so on. A fission chain reaction with the continuous release of energy is then possible. Fission can be caused by other particles, but neutrons are the only practical ones that result in sustained reaction, because 2 or 3 neutrons are usually released for each one absorbed by fission. This keeps the reaction going on. When the neutron is captured by a nucleus of an atom uranium 235, the uranium 236 isotope is formed. This isotopic, highly unstable type of uranium exists for perhaps 1/1,000,000th of a second. It split roughly into 2 equal parts and has a total energy release of 200 MeV. The product formed include the fission fragments, neutron and electromagnetic radiation or gamma rays. The fission products absorb most of the total energy released by the fission as kinetic energy, which is converted into heat. As the fragment collide, the particles decay mainly by beta and gamma radiation, with some neutron particle emission, and in rare earth causes alpha radiation. Most of the energy released as high close to site of fission and is released into surrounding. On the average, 2 or 3 neutrons are released with each fission. When the neutron causes fission uranium 235, a typical reaction produces barium krypton 2 or 3 neutron and releases of energy due to the loss of mass. An example: uranium 235 plus neutron gives barium 137 plus krypton 97 plus 2 neutron plus gamma radiation. The immediate product of fission reactions such as barium krypton above are called fission fragments. They are called fission products. It is the most important thing. The next important reaction is fusion. Fusion energy is form of nuclear energy released by the fusion combination of 2 light nuclei, that means nuclei of low masses, to produce heavier nucleus. The energy is produced in the sun and stars by continuous fusion reaction in which 4 nuclei of hydrogen fuse in a series of reactions involving other particles that continuously appear and disappear in the course of reaction. such as helium-3, nitrogen, carbon and other nuclei, but giving one nucleus of helium and 2 position. That means 4,1H1 gives 2He4 plus 2 base plus 1 e power 0, resulting in a decrease in mass about 0.0276 AMU, corresponding to 25.7 mega electron volt. The heat produced in this reaction maintains temperatures of the order of several million degrees in their cores and serves to trigger and sustain succeeding reactions. Artificially produced fusion may be accomplished when two light atoms fuse into large one, as there is a much greater probability of two particles colliding than of four. The 4 hydrogen reaction requires an average billions of years for completion, whereas deuterium reaction requires a fraction of a second. To cause fusion, it is necessary to accelerate the positively charged nuclei to high kinetic energy in order to overcome electrical repulsive forces by rising their temperature 200 of millions of degrees, resulting in a plasma. The plasma must be prevented from conducting the walls of container and must be confined for a period of time, that means of the order of a second, at a minimum density. Fusion reactions are called thermonuclear because very high temperatures are required to trigger sustain them. Of the several possible reactions between pairs of hydrogen isotope nuclei, the fusion of a deuterium nucleus or deuteron and a deuterium nucleus or deuteron has found to take place most readily. This is referred to as DT reaction and expressed by D plus T gives heavier nucleus, that means 4 helium plus small n plus 17.6 mega electron volt, whereas 4 helium represents a common helium-4 nucleus and n is neutron. The fusion of one deuteron and one triton releases 17.6 mega electron volt of energy. Next we will discuss about laser beam fusion. The initiation of nuclear fusion by laser beam was reported first from the USSR in 1968 and was subsequently confirmed by in the United States. However, the extent of fusion as indicated the neutron produced was very small. Laser beams of very much greater energy would be required to release a practical laser fusion reactor for generating useful power. Theory had indicated that laser beams of short wavelength radiation would provide the most efficient one of a DT fuel pellet. Consequently, neodymium ND glass, that means glass doped with a small amount of neodymium laser, have been used in basic studies of laser beam fusion. Because these lasers have a lower efficiency, smaller fraction of pumping energy is converted into radiation. A large proportion of the energy supplied is ineffectively. This energy is converted into heat, and the need for cooling the solid lasing material may take ND neodymium gas laser impractical for reactor use. An alternative is carbon dioxide gas laser. This has higher efficiency than neodymium class laser, and furthermore heat can be removed from the gas by circulation through an external cooling system. The radiation from the carbon dioxide laser has a long wavelength than from neodymium class laser, but it appears that this may not be such a drawback as had been thought. Exciting laser, no matter what the lasing material, are not powerful enough and do not have the other requirement for a fusion reactor. Efforts are being made to develop such lasers possible with novel lasing material. That means krypton fluoride is a best example for this. According to present estimate, a fusion power reactor would require a small laser system with an efficiency of at least 40%, capable of delivering 1 million joules, that means 0.28 kilowatt hour of energy per pulse in pulses of less than 10 to the power minus 9 second duration at a rate of 1 pulse per second. Laser fusion reactor. A laser beam fusion reactor is conceived as a strong spherical chamber of 2-meter radius. A small 1 mm dia pellet or sphere of a solid or liquid DT fuel is injected into a cavity when it reaches the center. The several symmetrically located high-energy laser beams are focused simultaneously on the fuel for about 10 to the power minus 9 seconds. An ablation occurs and fusion energy is released. After an interval of a second or so, another fuel pellet is injected and the process is repeated. The pellets acts miniature hydrogen bomb, exploding and delivering their energy to a wall and cooling medium. To cause the thermonuclear reaction, a beam of a laser light is divided into many components and directly simultaneously as a pulse nanosecond 10 to the power minus 9, that means 1 nanosecond duration, to bombard a pellet from several directions. The laser energy is absorbed in outer layer of the sphere, causing some material to be evaporated. The practical escaping from the surface impact a reaction momentum to the rest of the sphere. The resulting impulsion for force compresses the material to extremely high density, and the heating ignites the center of region of the pellet. The DT nuclear reaction proceeds outward to burn the rest of fuel and to cause the micro explosion that lasts about 20 picoseconds, that means 20 into 10 to the power 12 seconds. The kinetic energy of the products, neutrons and helium ions, is to be deposited over the surface of the container and out to a heat exchanger. This isolation of a reaction form walls is expected to prevent material damage. The helium nuclei formed in the fusion reaction are absorbed in the fuel, but the neutrons carrying 80% of fusion energy will escape. They are captured in the lithium blanket, where they deposit their energy as heat and also produce the tritium required as fuel material. The heat could be utilized to generate electricity in a more or less conventional manner by producing steam to drive a turbine generator. Apart from the actual fusion process, a laser beam cavity reactor would be similar in principle other nuclear fusion reactor. A problem is expected to arise from inner wall of a laser fusion cavity as a result of neutron bombarded. Proposed ways for overcoming this problem are to keep the inner wall continuously covered with a thin layer of liquid lithium, or to maintain of the liquid with the cavity. Although the fusion process initiated by laser beam would be self-sustained in a single DT fuel pellet, a continuous success of fresh pellet and laser beam pulse would be required to maintain operation of the reactor. A laser fusion reactor is thus a driven energy amplifier. The energy supplied in the short pulse of a laser radiation would be amplified by a factor of 100 or more in the resulting fusion reaction. Next, we move on to advantages of nuclear fusion. Some of the expected advantages of nuclear fusion as an energy sources are an ample supply of raw material for fuel, that means deuterium and tritium, at a moderate cost. The amount of fuel in the fusion system at any time would be so small that a large accidental release of energy would be impossible. Inherent safety with no danger of overheating if the cooling, that means heat removal system, should fail. Minimum problems of radioactive release to environment and of waste disposal. High thermal efficiency for the conversion of fusion energy into electrical energy because of high temperature which should be attainable. It is because of the above potential advantages that much effort is being expended in many countries in order to make fusion power a practical reality. Although the general requirements are well understood, many scientific and technological problems still remaining to be solved. Some important questions of this topic: what is fusion reaction? Next one is differentiate between fission and fusion. What are the main four fusion reactions which are considered for use in fusion reactors? Which one is most favorable reaction? Next one is what is the main advantage of DD reaction? Next one is what are the main conditions or requirements for thermonuclear fusion? Explain in brief. Next one is state the Lawson create, on what factors does it depend? Next one is what are the main methods of plasma confinement? Describe briefly. Next one is describe the magnetic confinement fusion considering DT reaction. Next question is describe the different methods of plasma heating. Next one is write short notes on magnetic heating, advantages of nuclear fusion, pellet fusion reactor, plasma heating, and cold fusion. Next question is describe the working of internal confinement fusion or pellet fusion reactor. Next one is what are the advantages of nuclear fusion? Okay, Dear student, now we are in the end of the unit 1. Thank you.